Hello everyone. In this lesson, we're going to learn about linear regression and how to perform linear regressions using Python. Now, in the last few lessons, we learned about statistical inference testing techniques such as the t-test, chi-squared test, and ANOVA test that you analyze differences between data samples. Predictive modeling describes using data samples that we already have to make predictions about data that we don't have yet. Now, linear regression is one of the most basic and foundational predictive modeling techniques that involves predicting a numeric target variable based on one or more explanatory variables. The term regression, when used in predictive modeling, generally refers to any task where you're trying to predict a real numbered target, as opposed to classification, where you're trying to predict a category or class. The term linear in the name linear regression refers to the fact that the method models data with a linear combination of explanatory variables. Basically, all that means is it takes each of the explanatory variables that you're trying to use to predict some target, and then each one is going to be multiplied by some weighting factor or coefficient, and then all of those weighted variables are going to be added together to arrive at the final prediction. So the basic formula for a linear regression can be seen here written out in actual words. So we're going to have some response or target variable that's going to be equal to an intercept term plus some constant or coefficient, which is going to be the weight term, times the explanatory variable. Now, in this example here, we only have one explanatory variable and one constant, but we could have many of those if we wanted to. Now, in its most basic form, what linear regression does is it fits a straight line to the data that minimizes the sum of squared differences or residuals between that line and the actual data points. We're not going to go into all the math behind how linear regression works in this lesson. It's mostly just meant to provide an overview of the technique and to show how to do it in Python. The most important thing to know is just that what regression is doing is finding the line that best fits the points based on the squared differences from the line that it fits. Now, it's important to note, since linear regression fits data with a line, it is most effective in cases where the response variable and explanatory variable or variables have a linear relationship. That is one of the basic assumptions of a linear regression model. So if they don't have a linear relationship, you might not get great results with a linear regression, and you might need to do something else, like use a different model or transform the data in some way so that the relationship is more linear. So to give an example of using linear regression in Python, we're going to load in some packages and a data set called the mtcars dataset. It just provides some information on different vehicles, such as their gas mileage, weight, and other characteristics. And we're going to create a regression model that's going to try to predict the MPG of the car, or the fuel efficiency, based on other features of the vehicle. So I'll just start by loading in these packages and then running this plot here that's just going to show us a scatter plot of the MPG variable. That's what we're going to try to predict, versus the weight variable. So the weight of a car versus the miles per gallon. Let's scroll down and see what it looks like. Maybe I'll zoom out so we can see it a little bit better here. So as we can see here, as the weight of a car goes up along the x-axis, the MPG of the car, or the fuel efficiency, the data points here seem to have a pretty noticeable downward or negative trend. So that implies that as cars get heavier, their fuel efficiency goes down. That aligns pretty closely with what we would expect. A big heavy vehicle, it's probably hard for it to get good fuel efficiency. So this looks like a task where a linear regression might come up with a pretty good predictive model for this. So to create a linear regression model for these data points, we are going to use the sklearn or scikit-learn library for Python. That is a very common predictive modeling library in Python that has functions for a whole host of predictive modeling tasks. But for our lesson here, we're pretty much just going to use it for linear regression. So we are going to say from sklearn, import the linear model. That will let us run a linear regression. And to initialize and then run the model, we just have to run through a few steps. So first, you initialize the model by saying linear model.linear regression. We're going to take this initialized model .fit. So now we're going to fit the model with our specific data. The x argument is the explanatory variables that you want to use, and then y is going to be equal to the target variable. So in this case, that was the miles per gallon column, so we're passing that in there. And then after we run this fit, we can check the various outputs from the model. So here we're going to print the intercept that it finds, so regression model.intercept. And then we're going to also print the coefficients that the model found. And when we run this, we see that we have an intercept of 37 or so miles per gallon and a coefficient for the weight variable of minus 5.3. So this coefficient here is telling us that as the weight of a car increases by 1 unit, the predicted miles per gallon of that car goes down by minus 5.3 miles per gallon. So that's basically showing us numerically what we saw in the plot earlier, that as weight goes up, the expected miles per gallon goes down. Now we can also get a sense of how good of a predictor this regression model is by using the model.score function. So to do that, we can take our regression model, run.score on it. Again, we'll pass in the data and the target. And the number output here is what's known as the r-squared value. This is a value that ranges between 0 and 1, and it denotes the proportion of variance in the dependent variable, so in this case miles per gallon, that is explained by the model or explained by the explanatory variables. So in this case, we have an r-squared of 0.75. That tells us that about 75% of the variance in the miles per gallon can be explained by the weight. Now this r-squared value is based on the residuals of the model. The residuals are just the differences between what the model or line drawn by the model predicts for each point and what the actual value is for each of those points. And we can extract the model's residuals by making predictions with the model on the data set. So here we're going to make a prediction using our data. So regression model.predict. For the data, we're just going to pass in the training data that we use to make the model. So that will create a prediction for miles per gallon for each of the cars in this data set. And then we can calculate the residuals just by taking the true miles per gallon, which is stored in the MPG column, and subtracting away our prediction. And if we run .describe on them, we can pull up a summary of the statistics for the residuals. Now we could have calculated that r-squared value by hand instead of making scikit-learn do it for us. The r-squared value is calculated as 1 minus the sum of squared residuals divided by the sum of squares total. The sum of squared residuals is the sum of the squares of the residuals that we calculated above, and the sum of squares total is the sum of squared differences between each data point and the mean of the data. So we could have calculated that by hand using this code here. So all we would have to do is calculate our sum of squared residuals. Well, we have our residuals already. We did that above. So we'll square those and sum them up. To calculate the total sum of squares, we just take the actual values, subtract away the mean from all of those actual values, square that and sum them all up. And now we have the SSR, the SST, to calculate r-squared. We just say 1 minus sum of squared residuals over sum of squares total. And if we run that calculation, we'll get the r-squared value, which should be the same as the one we got by running it in scikit-learn. Now that we have our linear model, let's plot the line that it fits to our data on the scatter plot we made earlier so that we can visually observe how well it fits to the data. Essentially, we're just adding a line to the plot we made earlier. So we'll scroll down and we can see this blue line now has been added to the plot. So in this case, linear regression seems like a reasonably good model for predicting MPG from the weight of a car. Now we mentioned that a linear relationship between the dependent variable and the explanatory variables is important for linear regression to work well. Another thing that is important to keep in mind is that since linear regression involves minimizing the sum of squared differences of these points to the line you're fitting, if you have a single point that's very far away from your line, well, since it's squared, that difference is magnified even more. So a single outlier point can have a disproportionately large influence on where this line is drawn. So you want to be careful about making linear regression models if your data set might have some outliers. We'll give an example of that by adding an outlier point to this data set and rerunning the plots here. So below, we're just going to rerun the model with an extra data point and rerun the plot. We're just adding one new car here called supercar that has a very high weight, so the weight's going to be set to 10, and I think that's in thousands of pounds or tons or something, so that's a super heavy car, but it also has a really good MPG. So this is going to constitute a major outlier, and when we rerun the model and rerun the plot, we're going to see that the line is going to be very different just because of the addition of this one outlier point. So we'll scroll down here. We can see our supercar way up here in the corner. So maybe this is some kind of crazy hybrid cyber truck or something that gets very good MPG because it runs partially on a battery. Who knows? But the single outlier point has taken what was a pretty clear negative relationship between MPG and weight and completely changed the line so that it actually has a positive slope now. Now, admittedly, this is an extreme contrived case. You probably won't see something quite this extreme in the real world, but it just goes to show you that if your data set has some outliers in it, it can have a significant negative impact on a linear regression model. So you should be checking for outliers before running a linear regression. Now, another thing to keep in mind is that with a well-behaved linear regression model, we'd like to see residuals, so essentially the errors that we're making in our predictions, we'd like those residuals to be roughly normally distributed. So we want the errors to kind of fall on both sides of the line. We'd also like the variance of those residuals to be constant across the various predictions. Now we can investigate the normality of our residuals using what's called a normal QQ plot or quantile-quantile plot. It's a type of plot that essentially lets you compare whether two distributions are roughly the same. So I'll show how to make a normal QQ plot against our residuals below. To do that, we're going to call stats.probplot. The first argument is going to be those residuals, and then for dist, we're going to say norm because we're interested in comparing it to a normal distribution. So if our residuals were completely normal, we would expect all of the points associated with them, these blue dots here, to fall right along this red line. So this divergence here from normality shown by our QQ plot at the tails here could be a little bit concerning because it appears that the residuals aren't completely normal. So there might be some transformation of the variables that could improve our model, but it doesn't seem so far off that this should be a completely unreasonable thing to do to predict miles per gallon. Now, after making predictions, it's useful to have some kind of metric to evaluate how well the model performed. Now, for linear regression, we can use the R-squared measure, but the R-squared measure can't be calculated necessarily for all types of models where you're predicting a numeric target. It does work for linear regression, but if you're comparing the performance of several different models, it'd be better to have some sort of universal evaluation metric that we can compare. So if we wanted to calculate a metric like that, one common thing we can do for a numeric prediction is calculate the root mean squared error. So basically the square root of the average squared deviations of the actual values from the predictions. So we actually calculated this value out. We wrote a function to do that way back in lesson 12. So I'll show you the code for doing that here. We're going to define a new function, RMSE, for root mean squared error. It takes the predicted values and the targets, the actual values, and then just returns the square root of the average of those squared residuals and returns it. So we can run this against our predictions and data here to get the value for this problem. So in this case, the root mean squared error is 2.94. So that's giving us some sense of, on average, about how far off are we. Now, you don't need to write your own custom function to do this. This is a very common thing to want to calculate. So instead of doing that, you can just import the mean squared error function from sci-kit learn and just do a square root or raise it to the half power. Now, in this simple example that we've shown here, there was a linear relationship between the dependent variable and the explanatory variables. Well, what if there was a different sort of a relationship, like a quadratic relationship or something that wasn't linear? Well, in that case, you can do something what's known as a polynomial regression, which essentially just means you're going to transform some of the explanatory variables by squaring them, cubing them, or doing other polynomial transforms on them, and then running the linear regression, adding those additional polynomial terms. So we'll give an example of how we could do a polynomial regression in Python by making a model where we're going to predict MPG both by the linear weight term that we had before, but we're also going to include an additional squared weight term, and maybe adding that additional squared term will allow us to capture some non-linearity in the relationship between the two variables. So to create a polynomial regression model, it's going to be a similar process to the simple linear regression. We're just going to add an extra variable with the squared term in it. All we're going to do is make a new predictors data frame that's going to add that extra variable. So here we're going to say predictors is going to be a data frame of our original explanatory variable, the weight column, but also a new column that is that same variable, but to the second power or squared. And now we're just going to refit the model and rerun everything just using this new data frame that has this extra term in it. So we're going to fit that model. We're going to print the intercept, the coefficients for it, and the r squared. So when we run all of this, you can see we have a new model intercept with some new coefficients. And most notably, the model r squared has now changed. We can see that the model has a 0.819 r squared, and before it was about 0.75. So that implies that this new model explains more, significantly more, of the variance in the dependent variable than the original model did. It should be noted, however, that adding additional predictor variables to a regression model can only ever increase the r squared. So you want to be careful of adding too many variables if it doesn't increase the r squared very much. There's actually an alternative measurement to r squared called the adjusted r squared that will account for adding additional variables like this. So when you're running a model that has many added variables, you would probably want to use the adjusted r squared instead of just the standard one. And just to get a sense of what this new model looks like, let's generate a new plot of it. So we can scroll down and check the new scatter plot, and we can see that the regression line that was found here is now not just a straight line. Because we included that squared term in it, the line actually has a curve that perhaps allows it to fit some of these data points for very heavy cars up at this end a little bit better than our original model that just went straight down here. One thing we have to be careful about here, though, is overfitting on the training data. Overfitting describes a situation where our model fits itself too closely to the data we use to create it, which is known as the training data. And this can result in poor performance or generalization when applying the model to new data. This is why we generally don't want to use our training data to evaluate the model itself. It gives us a biased result that's tends to be overly optimistic if we do that. So in practice, we generally want to hold out some testing data set that we can use to evaluate the model. But in this case, we didn't do that because we were just learning the basics of how to do linear regression. Now, one of the strengths of doing a linear regression that only includes, say, a first order and second order terms like the one we did here is that the model is so simple already that it's not that likely to drastically overfit the data. But if we were to make a more complex model with perhaps many more variables or higher order features, we could end up creating a pretty complicated model that's more prone to overfitting the data. So to give an example of doing that, let's recreate a polynomial regression model. But now we're going to include third, fourth, fifth, etc. order terms all the way up to 10. And we'll rerun the model and rerun a plot just to show you how complicated the model can get if you do something like that. So we don't have to inspect the code too much here. We're just going to create a new data frame that has all these additional terms in it and then rerun the model. So we'll do that here. And we can see that the model intercept even is something kind of fishy already because we have a huge negative number and we have coefficients that are kind of all over the place. But we will notice that the r squared here is larger as we would maybe expect because the more you increase the number of variables, the r squared is only going to go up. So that could perhaps be a bit misleading because it seems like, hey, the model might be performing better because we're seeing a higher r squared. But if we inspect a plot of the model, so we'll create a plot here, just visually we can tell that this model is probably doing something it shouldn't be. We kind of see the line going up and down a bit erratically, trying to fit itself as closely as it can to the points. And at this part here, it goes all the way down and all the way back up just in order to closely fit these last 3 points. Well, this big dip has nothing to do with any points that we have here. It's just the model kind of doing a weird thing in order to fit these last 3 points as well as it can using a 10th order polynomial. This is a clear sign of overfitting here because if we actually had a point we wanted to predict that was weight 5, this model here is telling us that a car with weight 5, which is probably either 5,000 or 5 tons, I'm not sure what the units are, but if we had a car with weight 5, this model would predict its miles per gallon is less than 0. So this is just an example of how making a model too complicated, giving it too much flexibility to fit to your training data, can actually make it fail to generalize well to new cases that aren't very similar to the ones you had in your training data set. Now you can include as many explanatory variables as you want to in a linear regression model. Adding more than one just means you're doing a multiple linear regression instead of a simple single linear regression. And all we have to do to run a multiple linear regression in code is just pass data that has more than one column into the linear regression function. We kind of already did that above with the polynomial regression, but that was a transformed version of the same variable we were already using. In this case, we'll just pass in 2 different variables. So we'll give an example here. We're going to predict MPG again, but now we're going to use both the weight column and the horsepower column. Maybe knowing the horsepower of the car will give us a little bit more information and it will result in a better model. So let's rerun this. We're going to initialize a new linear regression. We're going to fit it, but we're going to include 2 columns this time. And we'll just print out all the same output we've been doing. So we can see the new intercept. We can see the coefficients for the 2 things we passed in here. So it seems that both weight and horsepower have a negative relationship to the miles per gallon. That kind of makes sense because a car with a very big, powerful engine, the engine probably isn't super efficient. It's more geared toward getting a lot of power. And the r squared here is 0.826. So that is quite a bit higher than the model where we only had weight. Now, one question we might want to ask here is, well, does horsepower actually have a linear relationship to miles per gallon? This improvement suggests maybe it does, but let's check with a scatter plot. So I'll run a scatter plot of horsepower versus miles per gallon, and we can see that it seems to have a bit of a linear relationship, but maybe that's a little bit more quadratic because the effect seems to level off a bit as horsepower goes up. It seems to be maybe that's a curved relationship. So perhaps in this case, including a squared term for horsepower would get us some better results. So let's run one final linear regression model. We're going to include both the linear terms for weight and horsepower and also squared terms for both of those. And when we run all of this, we see a final model with an r² value of 0.98. That's the highest one we've seen so far, and root mean squared error, that's the lowest we've seen so far. So those results maybe give us some confidence that this is the best model that we've produced so far in this lesson. But without testing this model on data that wasn't used to train it, we can't really be sure of how well it might generalize to new data. So it is always important in practice to have some held out test data set that you can use to evaluate how well it's performing on data that wasn't used to create the model in the first place. Now you might be saying, hey, in this model we actually used 4 predictors here. So maybe this r² isn't quite as good as we think it is because adding more variables can only ever increase the normal r². So in this case, it might be better to look at the adjusted r² as well because we're starting to add more features. So we can also calculate that adjusted r² using this formula here. I'm not going to go through and read through it all in detail, but I've got it written here and I've got it implemented in code here. So basically, it's just based on our normal r², the number of observations we have, which is the length of the MPG column, and also how many predictors we're using. That comes in the denominator here as p, so we entered that as 4. And when we run this, we see the adjusted r² is 0.87, so it's a bit less than the r². It will always be at least a little bit less than the normal r², and it'll be lower for each additional predictor that you have. But still, even with this adjustment, this adjusted r² is higher than any of the normal r² values we saw for the other models. So in this case, we can be somewhat confident that this final regression model might be the best model we've made so far for predicting miles per gallon. So in this lesson, we learned about the basics of linear regression and how to run it in Python. Now, linear regression is one of the most common and useful techniques for making predictions on real numbered targets. And there are many variations and variants of linear regression that build upon the basics we showed here in this lesson that can account for some of the shortcomings of this basic linear regression and make it more robust against various problems like overfitting. It might not be the most accurate model that you can find for a lot of tasks that you might want to do, but it is a good place to start, especially if you don't have a whole lot of data to make a prediction with. Some of the more complicated models out there, like say neural networks or complicated decision tree models, tend not to work quite as well unless you have quite a bit of data to use. Whereas the simple linear regression model can work fairly well even with relatively little data. Now in the next lesson, we're going to turn our attention to a different sort of predictive modeling task, classification, which instead of predicting a real number like we did in this lesson, we're going to try to predict a target label. So give a classification or category. So for that, we're going to be revisiting the Titanic disaster dataset, where we're going to be creating predictive models to predict whether passengers on the Titanic survived or died in the crash. So thanks for watching, and I will see you again next time.